The Enrico Fermi Atomic Power Plant Unit 1 represented the culmination of 1960s American fast breeder reactor technology, embodying specific design philosophies that would prove both revolutionary and fatally flawed. Constructed on the western shore of Lake Erie, south of Detroit, Michigan, the facility was designed by Atomic Power Development Associates and operated by Detroit Edison as a 200 MW sodium-cooled fast breeder reactor, intended to demonstrate commercial viability of plutonium-breeding nuclear technology. The reactor's fundamental design premise rested on the assumption that fast neutron spectrum operation with metallic uranium fuel would provide inherently stable thermal hydraulic characteristics. The core contained 105 fuel assemblies arranged in a hexagonal pattern, each assembly housing multiple fuel pins of 0.158-inch outer diameter containing metallic uranium, alloyed with molybdenum, and clad in zircaloy. The fuel pins were positioned within square stainless steel ducts and surrounded by sodium metal, serving both as coolant and neutron spectrum modifier. The designers embraced a philosophy of passive safety through negative temperature coefficients and thermal inertia of the large sodium inventory. Primary system pressure operated at a modest 120 psia, with inlet temperature of 288 degrees Celsius and outlet temperature of 427 degrees Celsius. This thermal regime was selected to maximize thermal efficiency while maintaining temperatures well below sodium boiling, creating what designers believed was an inherently safe thermal envelope that could accommodate significant transients without approaching dangerous conditions. Central to the design philosophy was confidence in the reliability and interpretability of instrumentation systems. Each fuel assembly was monitored by thermocouples positioned in the upper plenum to measure coolant outlet temperature. These measurements were considered direct and unambiguous indicators of thermal conditions within individual assemblies. The instrumentation logic assumed that accurate temperature readings would provide operators with reliable situational awareness of core thermal distribution and early warning of any developing problems. The reactor control system operated on established principles derived from thermal reactor experience, emphasizing neutron flux control through control rod positioning and reactivity management. Operators were trained to maintain reactor power through rod position adjustments while monitoring neutron detectors for flux distribution and stability. This approach reflected confidence that reactivity control constituted the primary mechanism for managing reactor safety, with thermal hydraulics serving as a secondary consideration that would respond predictably to neutron physics changes. However, embedded within this design philosophy lay assumptions about component reliability and system behavior that had not been rigorously tested under all credible operating conditions. The reactor incorporated 6 small zircaloy flow distribution plates positioned at the bottom of the core inlet plenum. These plates were intended to direct sodium coolant flow uniformly upward through the fuel assemblies, ensuring adequate cooling for all core regions during normal and abnormal operating conditions. The flow distribution plates represented a critical vulnerability that contradicted the design philosophy of passive safety. According to available documentation, these plates were added as modifications during late stages of design development rather than integral components subjected to comprehensive safety analysis from project inception. The plates were classified as passive structural components that could not credibly affect reactor safety because they contained no moving parts and were not subject to active control or manipulation during operation. This classification reflected a fundamental misunderstanding of the relationship between passive component, reliability, and active safety function. While the plates contained no moving parts under normal circumstances, they were subject to thermal cycling, flow-induced vibration, and potential material degradation that could lead to mechanical failure. The design analysis did not adequately consider the consequences of plate detachment or repositioning under dynamic operating conditions. The attachment methodology for the flow distribution plates employed welding techniques, adequate for static structural loads, but potentially inadequate for the dynamic hydraulic forces present during reactor operation. The plates experienced temperature variations from ambient conditions during shutdown to approximately 300 degrees Celsius during operation, creating thermal stress cycles that could propagate fatigue cracks in weld joints over extended periods. Flow-induced vibration from sodium circulation added additional cyclic loading that compounded thermal fatigue effects. The failure to recognize these plates as safety-critical components created a gap in design rigor that would prove consequential. Primary reactor safety systems underwent extensive analysis, testing, and redundancy provisions to ensure reliable operation under all credible conditions. The flow distribution plates received minimal analysis because they were not perceived as systems capable of initiating or propagating safety-significant events. The reactor's monitoring and diagnostic capabilities reflected 1960s understanding of instrumentation, adequacy, and human factors considerations. Individual fuel assembly thermocouples provided point measurements of coolant temperature, but offered no direct indication of coolant flow rates through specific assemblies. The diagnostic logic assumed that temperature increases would manifest gradually and would be easily distinguished from instrumentation drift or electrical interference based on temperature magnitude and rate of change. Operator training emphasized neutron physics and reactivity control while providing limited instruction in thermal hydraulic system diagnosis. The training program focused on scenarios involving control system malfunctions, coolant pump failures, or steam generator problems rather than mechanical failures of internal reactor components. This training gap reflected the design assumption that internal mechanical failures represented incredible events that need not be considered during routine operations. The cognitive framework provided to operators positioned them to interpret reactor behavior through the lens of familiar failure modes rather than novel conditions outside their training experience. When multiple simultaneous anomalies occurred, operators were trained to prioritize the most significant indication while attributing secondary anomalies to instrumentation problems or electrical interference. This approach was rational for managing routine equipment issues, but could delay appropriate response to complex events involving unfamiliar failure mechanisms. The reactor containment and emergency response systems represented the most robust aspect of the design, incorporating defense-in-depth principles that would prove effective during the actual incident. Automatic containment isolation systems were designed to respond to radiation detection, providing reliable protection against radioactive release, even under severe fuel damage conditions. These systems reflected appropriate recognition of the potential consequences of core damage and the necessity of preventing environmental contamination under all circumstances. The fundamental vulnerability created by the design philosophy lay in the disconnect between confidence in individual component reliability and understanding of system-level behavior under degraded conditions. The designers correctly recognized that fast reactor technology required sophisticated safety analysis and robust containment systems. However, they failed to adequately consider the potential for seemingly minor components to create conditions leading to fuel damage despite proper operation of primary safety systems. This design premise established the technical and cognitive conditions under which accurate instrumentation could provide misleading operational guidance. The thermocouples would function correctly by measuring actual coolant temperatures. The neutron detectors would function correctly by measuring actual flux levels. The control systems would function correctly by responding to operator commands. Yet the integration of this accurate information into situational awareness could fail catastrophically if the diagnostic framework was inadequate for interpreting complex system interactions involving mechanical failures of components not recognized as safety critical. The Zircaloy flow distribution plates represented the technical embodiment of this philosophical failure. Their classification as passive, non-safety-related components excluded them from the rigorous design analysis applied to primary safety systems, yet their mechanical integrity was essential for maintaining adequate cooling to all fuel assemblies. When one plate eventually failed through fatigue mechanisms not anticipated during design, it would create flow blockage conditions that could not be detected through existing instrumentation until fuel damage was already occurring. The Fermi 1 reactor operated for several months prior to October 5, 1966, under conditions that systematically conditioned operators to misinterpret thermal anomalies and established organizational patterns that would prove catastrophic when genuine thermal hydraulic problems developed. These latent conditions were not design defects in the conventional sense, but rather gaps between theoretical reactor behavior and actual operating experience that accumulated without recognition or correction. Beginning in the months preceding the incident, operators observed intermittent temperature anomalies during reactor operation that established a dangerous pattern of interpretation and response. Two fuel assemblies consistently indicated outlet coolant temperatures higher than normal during low-power operations. When reactor engineers investigated these anomalies by relocating the suspect fuel assemblies to positions under different thermocouples, the temperature readings did not correlate with the physical location of the assemblies, but remained associated with specific thermocouple positions. This pattern of investigation results created a compelling case for attributing temperature anomalies to electrical rather than thermal causes. The evidence appeared to demonstrate conclusively that thermocouples were unreliable indicators of actual thermal conditions, and that temperature readings exceeding normal ranges should be dismissed as instrumentation artifacts rather than investigated as potential thermal hydraulic problems. Operators developed confidence in this interpretation because it was supported by systematic testing that seemed to rule out genuine thermal causation. The cognitive impact of this experience extended far beyond simple equipment reliability concerns to fundamental assumptions about the relationship between instrumentation and reactor state. Operators learned through direct experience that temperature indications could not be trusted when they conflicted with expected reactor behavior. This learning was not irrational, but was based on observable evidence that had been systematically investigated by qualified reactor engineers, who concluded that the anomalies represented electrical rather than thermal phenomena. The training program for Fermi 1 operators reflected 1960s understanding of fast reactor operation and emphasized neutron physics over thermal hydraulic diagnostics. Operators received extensive instruction in reactivity control, control rod worth calculations, and neutron flux interpretation. They learned to manage reactor power through rod positioning, and to interpret neutron detector readings as primary indicators of reactor state and safety margins. Thermal hydraulic training focused on whole-core heat removal through the primary cooling system rather than individual fuel assembly thermal conditions. Operators understood the relationship between reactor power and bulk coolant temperature rise, and they were trained to monitor primary loop temperatures as indicators of heat removal adequacy. However, they received limited instruction in diagnosing thermal problems affecting individual fuel assemblies or in recognizing flow-related thermal transients that might not manifest in whole-core parameters. This training emphasis reflected the design philosophy that positioned neutron physics as the primary safety concern for fast reactor operation. Control rod reactivity worth, neutron flux distribution, and power level management were considered the critical skills for safe reactor operation. Thermal hydraulic considerations were treated as secondary effects that would respond predictably to neutron physics changes and could be managed through established heat removal systems. The control room design incorporated 1960s human factors understanding with emphasis on providing comprehensive information rather than integrated situational awareness. Operators worked with arrays of individual indicators displaying neutron flux, temperature, pressure, and flow parameters without synthesized displays showing the relationships between these measurements. Temperature readings appeared as numerical values without trend information or visual representation of spatial distribution across the core. This interface design required operators to mentally integrate multiple information sources to develop understanding of reactor conditions. During normal operation, this approach functioned adequately because parameter relationships followed predictable patterns that operators could recognize through training and experience. However, during abnormal events involving unfamiliar parameter combinations, the interface provided no assistance in synthesizing complex information into coherent situational awareness. The alarm system design created additional challenges for operator cognition during transient conditions. The control room incorporated multiple independent alarm systems for neutron flux, temperature, pressure, and radiation monitoring. Each system activated based on predetermined setpoints without integration or prioritization logic to guide operator attention during events involving multiple simultaneous alarms. During normal operation, individual alarms provided clear guidance for operator response because they typically activated independently in response to specific equipment malfunctions or parameter deviations. However, during complex events involving multiple simultaneous parameter changes, the alarm system could create information overload that hindered rather than assisted operator decision-making by providing numerous individual alerts without synthesis or prioritization. The organizational culture at Fermi 1 emphasized operational continuity and systematic problem-solving under uncertainty. Operators were encouraged to maintain reactor operation whenever safely possible and to investigate anomalies through methodical testing and analysis rather than immediate shutdown. This approach was appropriate for managing routine equipment issues and minor instrumentation problems, but could introduce delays during rapidly developing events requiring immediate protective action. The culture reflected the pioneering nature of the Fermi 1 project as a demonstration reactor intended to advance fast breeder technology through operational experience. The operating organization understood that minor problems and unexpected behavior were inevitable aspects of operating prototype technology, and that learning from these experiences was essential for advancing the technology. This perspective encouraged thorough investigation of anomalies rather than conservative responses that might limit operational experience. The interface between operations personnel and reactor engineering staff created communication structures that affected the interpretation and response to abnormal indications. Operations staff reported anomalies to engineering personnel who analyzed the data and provided recommendations for continued operation or shutdown. This process functioned well for routine issues that could be analyzed systematically over extended periods, but could introduce critical delays during events requiring immediate decision-making. The communication process reflected the technical complexity of fast reactor systems and the specialized expertise required for thermal, hydraulic, and neutron physics analysis. Operations personnel were trained to recognize abnormal conditions and implement immediate response actions, while engineering staff provided detailed analysis of complex technical issues. However, this division of responsibilities could create gaps in real-time decision-making when events developed more rapidly than the analysis process could accommodate. Maintenance and surveillance practices at Fermi 1 followed established nuclear industry standards for reactor internals, but did not include specific provisions for monitoring the mechanical integrity of flow distribution plates or other passive structural components. Routine inspections focused on primary system components, such as control rod drives, coolant pumps, and heat exchangers that were recognized as safety-critical systems requiring regular surveillance. The maintenance philosophy reflected the classification of flow distribution plates as passive structural components that could not credibly fail in ways affecting reactor safety. These components were not included in routine inspection programs because they contained no moving parts and were not subject to active manipulation during operation. The maintenance organization had no reason to suspect that mechanical failure of these plates could create safety-significant consequences. Procedure development for abnormal operating conditions emphasized response to design basis events such as control rod drive failures, coolant pump trips, or steam generator tube leaks. Emergency procedures provided clear guidance for managing these events through established response sequences that had been analyzed and validated through engineering analysis. However, procedures did not address events involving mechanical failure of internal reactor components or debris-induced flow restrictions, because such events were not considered credible during design development. The procedural framework functioned effectively for managing events within the design basis, but provided limited guidance for diagnosing and responding to novel conditions involving unfamiliar failure mechanisms. Operators faced events outside their training experience without clear procedural direction, requiring them to apply general principles and engineering judgment rather than established response sequences. Regulatory oversight of the Fermi 1 facility focused on compliance with design requirements and operational limits without specific attention to the potential for mechanical failure of passive internal components. The Atomic Energy Commission review process concentrated on primary safety systems, containment adequacy, and emergency response capabilities while treating flow distribution plates as structural components outside the scope of detailed safety analysis. This regulatory approach reflected contemporary understanding of reactor safety analysis and the appropriate scope of safety-related systems. Regulatory attention focused on systems capable of initiating or mitigating accidents rather than passive components that were not perceived as having safety significance. The regulatory framework had no mechanism for identifying or addressing the potential safety implications of components classified as non-safety related. The combination of these latent conditions created a systematic bias toward misinterpreting genuine thermal hydraulic problems as instrumentation anomalies. Operators had been conditioned through direct experience to distrust temperature indications that conflicted with expected reactor behavior. Training emphasized neutron physics over thermal hydraulics. Procedures provided no guidance for mechanical blockage events. The organizational culture encouraged continued operation during anomalous conditions. The regulatory framework excluded flow-critical components from detailed safety analysis. These conditions were not individual failures, but represented systematic gaps between design assumptions and operational reality. Each element was rational within its specific context and reflected appropriate application of contemporary nuclear technology understanding. However, their combination created conditions under which accurate instrumentation could provide misleading situational awareness and trained responses could amplify rather than mitigate developing problems. The critical vulnerability lay in the assumption that systematic investigation of anomalies would reveal their true nature and guide appropriate response. The investigation of previous temperature anomalies had concluded that such indications represented electrical rather than thermal phenomena, creating confidence that similar future anomalies could be safely dismissed. This confidence was supported by engineering analysis and appeared to be validated by subsequent reactor operation without adverse consequences. However, the investigation methodology was inadequate for distinguishing between electrical anomalies and genuine thermal hydraulic problems that might manifest in similar ways until they progressed to severe conditions. The testing approach focused on correlating temperature indications with fuel assembly positions rather than investigating potential flow restriction mechanisms that might affect thermal conditions without immediately visible symptoms. This gap in investigative methodology would prove crucial when genuine flow blockage conditions developed that could not be detected through existing diagnostic techniques until fuel damage was already occurring. On October 5, 1966, at 3 p.m., the Fermi 1 reactor was operating at 20 MWF during a planned power ascension to 67 MWF, representing routine testing within established operating parameters. The reactor had demonstrated stable operation at power levels up to 100 MWF in preceding weeks, and the planned ascension represented normal progression toward full power capability. Control rod positions were appropriate for the power level, with reactor coolant inlet temperature maintained at 288 degrees Celsius and bulk outlet temperature at 315 degrees Celsius according to established thermal hydraulic relationships. The first indication of developing abnormal conditions manifested at exactly 3 p.m. as erratic neutron flux signals on reactor instrumentation. The neutron detectors displayed irregular fluctuations that departed from the stable readings expected during steady-state operation at constant power. These fluctuations were not dramatic excursions beyond normal operating ranges, but rather subtle variations in detector output that suggested changes in neutron flux distribution or detector response characteristics. Operators interpreted these neutron signal irregularities through the cognitive framework established by previous operational experience and training emphasis on electrical system reliability. Similar detector fluctuations had been observed during prior reactor operation and had been successfully resolved through temporary conversion to manual reactor control. The standard response was to remove the reactor from automatic control, observe whether fluctuations ceased, and then restore automatic control if conditions stabilized. This interpretation reflected rational application of established troubleshooting methodology for instrumentation anomalies. Electrical interference or control system malfunction represented the most likely explanations for detector fluctuations, and manual control operation provided an effective test of this hypothesis. If fluctuations ceased during manual operation, electrical causation would be confirmed. If fluctuations continued during manual operation, instrument failure would be indicated. The reactor was placed on manual control at 3 p.m., and the neutron flux fluctuations disappeared as expected for electrical interference causation. This response pattern matched previous experience with similar anomalies and provided apparent confirmation that the problem involved control system electronics rather than actual changes in reactor neutron physics. Automatic control was restored after the fluctuations ceased, and normal power ascension was resumed according to planned operating sequence. However, the neutron detector fluctuations were actually providing early indication of changes in core neutron flux distribution caused by mechanical movement of debris within the reactor vessel. The detached zircaloy flow distribution plate was responding to hydraulic forces from sodium coolant circulation and was beginning to approach positions where it could affect coolant flow through individual fuel assemblies. The neutron flux changes reflected subtle alterations in neutron multiplication and absorption patterns as thermal hydraulic conditions changed in localized core regions. The diagnostic failure occurred because the symptom pattern matched established experience with electrical anomalies while the actual causation involved mechanical phenomena outside the operator's training and procedural framework. The neutron detectors were functioning correctly by measuring actual flux variations, but the interpretation logic was inadequate for recognizing mechanical debris effects on neutron physics. The successful response to manual control operation appeared to confirm electrical causation, but actually reflected temporary changes in hydraulic conditions that reduced detector fluctuations without addressing the underlying mechanical problem. At 3:05 p.m., with reactor power stabilized at 27 MWe, the erratic neutron signals returned despite continued manual control operation. This development should have indicated that the previous interpretation was incorrect and that the fluctuations reflected actual reactor physics changes rather than electrical interference. However, operators maintained their electrical causation hypothesis because it remained the most plausible explanation within their conceptual framework for reactor behavior. The persistence of neutron fluctuations during manual control operation represented a critical diagnostic indicator that required fundamental reassessment of the situation. Electrical interference should not have affected detector response during manual operation because the control system electronics were not actively manipulating reactor parameters. The continued fluctuations indicated either detector hardware failure or actual changes in neutron flux distribution that required investigation of reactor physics rather than electrical systems. Simultaneously with the returned neutron fluctuations, operators observed that control rods were positioned further withdrawn than normal for the 27 MWe power level. This indication suggested that additional reactivity was required to maintain the desired power level, implying either an unexpected reactivity loss or changes in neutron flux distribution that affected the relationship between rod position and power level. Under normal circumstances, rod position should correlate predictably with power level based on established reactor physics relationships. The abnormal rod positioning provided additional evidence that actual reactor physics changes were occurring rather than simple electrical interference with instrumentation. Reactivity changes sufficient to require modified rod positions indicated physical alterations in core conditions that should have triggered investigation of potential mechanical problems. However, operators interpreted the rod position anomaly as confirmation of instrumentation problems rather than recognition of genuine reactor physics changes. The cognitive challenge facing operators was the integration of multiple simultaneous anomalies that individually could be explained by familiar failure modes, but collectively indicated unfamiliar conditions requiring different diagnostic approaches. Neutron fluctuations could be explained by electrical interference. Abnormal rod positions could be explained by instrument calibration drift. However, the simultaneous occurrence of both symptoms should have suggested systematic changes in reactor conditions that required comprehensive investigation. During this same period, thermocouples monitoring individual fuel assembly outlet temperatures began indicating readings of 370 degrees Celsius and 380 degrees Celsius for two specific assemblies, compared to the bulk coolant temperature of 315 degrees Celsius. These readings represented temperature increases of 55 degrees Celsius and 65 degrees Celsius above normal conditions, far exceeding typical measurement variations and indicating genuine thermal conditions requiring immediate attention. However, operators interpreted these temperature indications within the context of previous experience with unexplained temperature anomalies that had not correlated with actual thermal conditions. The months of prior operation with similar temperature readings that had been investigated and attributed to electrical causes created cognitive bias against accepting thermal indications as valid measurements of actual fuel assembly conditions. The temperature readings were technically accurate measurements of actual coolant conditions above the affected fuel assemblies. The thermocouples were functioning correctly by detecting elevated coolant temperatures resulting from reduced flow through assemblies affected by the partially detached flow distribution plate. However, the diagnostic framework was inadequate for distinguishing these genuine thermal indications from the electrical anomalies that had been observed previously. The physical reality during this period involved progressive positioning of the loose zircaloy plate into configurations that increasingly restricted coolant flow through specific fuel assemblies. The plate was responding to hydraulic forces from sodium circulation and thermal expansion effects that moved it into more restrictive positions as reactor power and coolant flow increased. The flow restriction was creating thermal imbalances between heat generation and heat removal in the affected assemblies. The flow blockage was not complete, but was sufficient to create local thermal conditions that exceeded normal operating parameters. The reduced coolant flow through blocked assemblies caused temperature increases that were detected by outlet thermocouples and resulted in thermal hydraulic conditions that affected local neutron physics. The neutron flux fluctuations reflected changes in neutron multiplication and absorption caused by altered thermal conditions in the blocked regions. The critical period from 3:05 p.m. to 3:09 p.m. represented the window during which accurate instrumentation was providing valid indication of developing emergency conditions, but the diagnostic framework was leading operators to dismiss these indications as instrumentation anomalies rather than genuine reactor problems. The neutron detectors, control rod position indicators, and temperature thermocouples were all functioning correctly and providing accurate measurements of actual reactor conditions. However, the integration of this accurate information into situational awareness was failing because the interpretation logic was optimized for familiar failure modes rather than mechanical debris effects. Operators possessed the technical information necessary to recognize developing fuel damage conditions, but their training and experience provided no framework for interpreting mechanical blockage symptoms that manifested as combinations of neutron, reactivity, and thermal anomalies. The divergence between reactor state and operator perception reached critical proportions during this period as actual thermal hydraulic conditions approached fuel damage thresholds, while operators maintained confidence in electrical causation hypotheses. The reactor was progressing toward fuel cladding failure through thermal mechanisms that could not be corrected through control rod manipulation or electrical system repairs. At 3:09 p.m., building ventilation radiation monitors activated, providing unambiguous confirmation of radioactive material release from fuel damage. This alarm represented the first indication that definitively confirmed actual reactor problems rather than instrumentation anomalies and required immediate recognition that previous symptom interpretation had been fundamentally incorrect. The radiation alarm activation at 3:09 p.m. marked the definitive transition from ambiguous symptoms to confirmed fuel damage, triggering automatic containment isolation and forcing immediate recognition that previous interpretations of reactor conditions had been fundamentally incorrect. The building ventilation radiation monitors detected airborne radioactive materials that could only originate from breached fuel cladding, providing unambiguous confirmation that genuine thermal hydraulic problems were occurring rather than electrical instrumentation anomalies. The physical progression leading to this alarm involved complex thermal hydraulic and materials science phenomena that had developed over the preceding 9 minutes as the detached zircaloy flow distribution plate moved into increasingly restrictive positions, affecting coolant flow through specific fuel assemblies. The mechanical blockage created thermal imbalances between nuclear heat generation and coolant heat removal that progressed through predictable stages toward fuel damage conditions. The initial stage of thermal progression involved local coolant temperature increases as reduced flow through blocked assemblies created heat removal inadequacy. The metallic uranium fuel continued generating nuclear heat at rates determined by neutron flux and fission cross-sections, but the available coolant flow was insufficient to remove this heat at normal temperature levels. The thermal imbalance manifested as outlet coolant temperature increases that were accurately measured by thermocouples and correctly reported to operators. The second stage involved fuel temperature increases as thermal conduction from fuel to coolant became inadequate to maintain fuel temperatures within normal operating ranges. Metallic uranium fuel exhibits thermal expansion characteristics that can exacerbate flow restriction effects by reducing flow channel dimensions as fuel temperature increases. The fuel pins expanded radially as temperatures rose, potentially creating additional flow resistance that amplified the thermal imbalance initiated by the debris blockage. The sodium bond between fuel and cladding represented another critical thermal hydraulic component that affected heat transfer characteristics under reduced flow conditions. As fuel temperatures increased, the sodium bond could approach boiling temperatures, creating vapor spaces that degraded heat transfer from fuel to cladding. The reduced heat transfer efficiency further accelerated fuel temperature increases and created positive feedback mechanisms that made thermal conditions progressively worse once critical thresholds were exceeded. The third stage involved cladding temperature increases as heat transfer from fuel through the degraded sodium bond and reduced coolant flow could no longer maintain cladding temperatures within material design limits. Zircaloy cladding exhibits predictable thermal behavior, with mechanical property degradation beginning at temperatures above approximately 650 degrees Celsius and rapid oxidation occurring above 850 degrees Celsius under reactor environment conditions. The progression toward cladding failure involved multiple competing physical mechanisms that determined the timing and mode of eventual breach. High-temperature oxidation created oxide layers on cladding surfaces that reduced effective wall thickness and degraded mechanical properties. Thermal stress from temperature gradients and differential thermal expansion created mechanical loading that approached ultimate strength limits of the oxidized cladding material. The neutron physics effects observed during this progression reflected changes in neutron multiplication and absorption characteristics as thermal hydraulic conditions evolved within the affected core regions. The metallic uranium fuel exhibited positive temperature coefficients of reactivity, meaning that fuel temperature increases caused reactivity increases that required additional control rod insertion to maintain constant power levels. This effect explained the abnormal rod positioning observed by operators as compensation for reactivity changes in overheated fuel regions. Simultaneously, sodium voiding in overheated regions affected neutron spectrum and multiplication characteristics through changes in neutron moderation and absorption. Sodium normally provides significant neutron absorption in fast reactor spectra, and voiding caused by elevated temperatures reduced this absorption, creating additional positive reactivity effects. However, sodium also provides some neutron moderation, and voiding reduced thermalization effects that could create negative reactivity contributions in some spectral regions. The competing reactivity effects from fuel temperature increases and sodium voiding created complex neutron flux distribution changes that manifested as the detector fluctuations observed by operators. Different neutron detectors positioned around the reactor vessel responded differently to local flux changes depending on their geometric relationship to the affected fuel assemblies and their neutron energy response characteristics. The critical thermal threshold for cladding failure was reached when local fuel temperatures exceeded approximately 1,000 degrees Celsius, creating thermal conditions that could not be sustained by zircaloy cladding material under reactor environment conditions. The combination of high-temperature oxidation, thermal stress, and mechanical loading from internal pressure caused initial cladding breaches that allowed fission products to escape from fuel pins into the coolant system. The fission product release mechanism involved both immediate release of volatile isotopes that had accumulated in fuel pin void spaces and longer-term release of less volatile species through diffusion and dissolution processes. The initial release consisted primarily of noble gases such as xenon and krypton that could rapidly disperse through the coolant system and potentially reach containment atmosphere monitoring systems. The detection of airborne radioactivity at 3:09 p.m. indicated that fission products had been transported from the damaged fuel assemblies through the primary coolant system to locations where they could be detected by building ventilation monitors. This transport required several minutes for fission products to circulate through primary coolant loops, pass through cover gas systems, and reach detection points in building ventilation systems. The thermal analysis performed during post-incident investigation confirmed that the observed progression from initial flow blockage to fuel damage was consistent with calculated thermal hydraulic conditions under partial flow restriction scenarios. The metallic uranium fuel properties, sodium coolant characteristics, and zircaloy cladding behavior all performed according to established materials data when subjected to the thermal conditions created by debris blockage. The mass balance analysis revealed that fuel melting was localized to specific regions within two adjacent fuel assemblies, where flow restriction was most severe. The total quantity of damaged fuel represented a small fraction of core inventory, indicating that thermal damage did not propagate beyond the immediately affected assemblies during the time period before reactor shutdown. The limited extent of damage reflected the effectiveness of prompt shutdown and terminating nuclear heat generation before thermal conditions could spread to adjacent fuel regions. The investigation revealed physical evidence confirming the flow blockage mechanism through examination of the reactor vessel internals and damaged fuel assemblies. Metallurgical analysis of recovered fuel pins showed evidence of high-temperature exposure consistent with calculated thermal conditions under reduced coolant flow. Cladding examination revealed oxidation patterns and mechanical failure modes characteristic of thermal stress failure at elevated temperatures. The loose zircaloy plate was eventually discovered during systematic inspection of reactor internals in October 1967, more than 1 year after the incident. The plate was found in the inlet plenum positioned in a configuration consistent with partial flow blockage to the fuel assemblies that had experienced damage. Metallurgical examination of the plate revealed fatigue crack patterns indicating failure through thermal cycling and flow-induced vibration over extended operating periods. The failure analysis demonstrated that the plate detachment had occurred gradually through fatigue mechanisms rather than sudden mechanical overload. The crack propagation patterns suggested that initial cracking had developed over multiple thermal cycles, with final separation occurring when crack growth reached critical dimensions for the applied loading conditions. This gradual failure mode explained why the blockage effects were not immediately evident, but developed progressively as the loose plate moved into more restrictive positions. The thermal hydraulic modeling performed during incident reconstruction showed that complete flow blockage would have led to fuel melting within approximately 2 minutes, while partial blockage created conditions allowing gradual temperature increases over longer time periods. The October 5 event likely involved partial blockage that became progressively more severe as thermal expansion and debris positioning effects further reduced flow through the affected assemblies. The physics analysis confirmed that accurate instrumentation had provided valid measurements of actual reactor conditions throughout the event sequence. The neutron detectors correctly measured flux distribution changes caused by thermal hydraulic effects in blocked fuel assemblies. The thermocouples correctly measured elevated coolant temperatures resulting from reduced flow and increased fuel heat transfer. The control rod position indicators correctly reflected reactivity changes required to compensate for temperature coefficient effects in overheated fuel. The failure of operators to recognize these accurate measurements as indications of developing emergency conditions reflected inadequacy of diagnostic frameworks rather than instrumentation problems or operator errors. The measurement systems functioned correctly by providing accurate data about actual reactor conditions. The failure occurred in translation of accurate measurements into appropriate understanding of thermal hydraulic phenomena that were outside the operator's training and procedural guidance. The radiation alarm activation at 3:09 p.m. triggered immediate implementation of emergency response procedures that had been extensively planned and practiced, but never tested under actual fuel damage conditions. The automatic containment isolation system responded within seconds to airborne activity detection, sealing the reactor building from the external environment, and activating filtered ventilation systems designed to prevent radioactive release. This response demonstrated the effectiveness of defense in-depth safety principles despite the failure to prevent fuel damage. The containment isolation sequence involved closure of ventilation inlet and outlet dampers, shutdown of normal ventilation fans, and startup of emergency filtered exhaust systems designed to maintain slight negative pressure within the containment while processing any airborne radioactivity through high-efficiency filtration. The system functioned exactly as designed, establishing containment integrity that would prove essential for preventing environmental consequences of the fuel damage. Simultaneously with containment isolation, operators initiated reactor power reduction procedures to minimize nuclear heat generation driving the fuel damage process. The reactor power was decreased from the peak level of 31 MWth reached during the power ascension to 26 MWth by 3:20 p.m. through control rod insertion. However, the power reduction could not immediately reverse the thermal hydraulic conditions within the blocked fuel assemblies, because the mechanical flow restriction remained in place. The decision to reduce power rather than implement immediate reactor shutdown reflected operators' continued uncertainty about the severity of conditions and their training emphasis on maintaining reactor operation whenever possible. Emergency procedures provided guidance for power reduction as an initial response to abnormal conditions, with shutdown reserved for situations requiring immediate cessation of nuclear reactions. The radiation alarm indicated fuel damage but did not necessarily require immediate shutdown if conditions could be stabilized through power reduction. This approach reflected rational application of emergency procedures under conditions of incomplete information about the extent and progression of fuel damage. Power reduction would decrease nuclear heat generation and provide thermal margin that might allow damaged fuel to stabilize at safe temperatures. Complete shutdown would eliminate nuclear heat generation, but would also complicate subsequent analysis of reactor conditions and potentially create additional challenges for long-term cooling under damaged conditions. The manual reactor shutdown was implemented at 3:20 p.m., when continued monitoring indicated that power reduction was insufficient to stabilize conditions, and that radioactive release was continuing despite reduced power levels. Control rods were fully inserted to terminate nuclear reactions and establish subcritical conditions that would allow decay heat to decrease, according to established time-dependent relationships. The post-shutdown period presented complex challenges related to verifying adequate cooling under unknown damage conditions and assessing the extent of fuel damage and radioactive material release. Normal shutdown cooling procedures assumed intact fuel geometry and predictable heat removal through established flow paths. The unknown extent of fuel damage created uncertainty about coolant circulation effectiveness and heat removal adequacy that required modified monitoring approaches. Primary coolant circulation was maintained through operation of electromagnetic pumps in all three primary loops, ensuring continued heat removal from the reactor core through intermediate heat exchangers. Coolant temperature monitoring indicated gradual reduction in core outlet temperatures consistent with expected decay heat characteristics, suggesting that bulk cooling was adequate despite local damage in specific fuel assemblies. However, significant uncertainty remained regarding thermal conditions within the damaged fuel assemblies and the potential for continued degradation during the post-shutdown period. The blocked coolant flow that had initiated the thermal transient remained in place, and reduced coolant temperatures during shutdown conditions might not provide adequate heat removal if significant fuel geometry changes had occurred during the damage progression. Radiation monitoring throughout the facility provided crucial information about the extent and location of radioactive material release, while demonstrating the effectiveness of containment systems in preventing environmental consequences. Containment atmosphere monitoring detected elevated airborne activity levels consistent with volatile fission product release from damaged fuel assemblies. Area radiation monitors within the reactor building showed increased readings indicating contamination of accessible areas within containment. Primary coolant sampling revealed elevated activity levels, confirming continued leakage of radioactive materials from compromised fuel cladding into the sodium coolant system. chemical analysis of coolant samples provided information about the isotopic composition of released fission products, indicating the types of fuel damage that had occurred and the extent of cladding breach in the affected assemblies. The radioactivity data demonstrated that approximately 10,000 curies of fission products had been released from damaged fuel into the primary coolant system. This quantity represented a significant fraction of the volatile fission product inventory in the affected fuel assemblies, but constituted a small percentage of total core fission product inventory. The limited release confirmed that fuel damage was localized to specific assemblies rather than widespread throughout the core. The containment systems successfully prevented release of radioactive materials to the environment despite the significant fission product inventory released from damaged fuel. Air sampling outside the containment boundary detected no elevated radioactivity levels, confirming that containment isolation and filtered ventilation systems were functioning effectively to protect public health and safety. The investigation of reactor conditions during the stabilization period required sophisticated diagnostic techniques to assess core geometry and fuel integrity without removing damaged assemblies from the reactor vessel. Neutron flux mapping using movable detectors provided information about reactivity distribution and potential changes in core configuration. Gamma radiation surveys indicated the location and intensity of radioactive material deposits within the primary system. The decision to maintain the reactor in safe shutdown condition while conducting detailed investigation reflected the complexity of assessing damage extent without creating additional hazards through fuel handling operations. Removing damaged fuel assemblies for examination would require specialized equipment and procedures to prevent additional cladding failure and radioactive contamination during handling and transport operations. Temperature monitoring throughout the post-shutdown period indicated stable thermal conditions with continued cooling adequacy, despite the presence of damaged fuel and unknown core geometry changes. Decay heat removal through the primary cooling system maintained fuel temperatures well below levels that could cause additional damage, providing confidence that immediate safety was assured through established cooling mechanisms. The long-term challenge involved developing procedures for eventual inspection and repair of reactor internals under high radiation conditions created by fission product contamination. The primary system would require extensive decontamination before personnel could access reactor vessel internals for detailed examination of damage extent and removal of damaged fuel assemblies. Engineering analysis during the stabilization period focused on thermal hydraulic modeling to predict cooling adequacy under various assumptions about fuel geometry and flow distribution changes. Conservative analyses assumed significant flow blockage and fuel geometry distortion to ensure that cooling calculations provided adequate safety margin even under pessimistic damage scenarios. The stabilization phase demonstrated both the effectiveness of engineered safety systems and the challenges associated with managing fuel damage events in fast reactor systems. Automatic containment isolation prevented environmental release of significant radioactive material inventories. Primary cooling systems maintained adequate heat removal despite local fuel damage and unknown core geometry changes. Emergency procedures provided appropriate guidance for immediate response actions. However, the stabilization period also revealed limitations in diagnostic capabilities for assessing reactor conditions under damaged configurations, and gaps in procedures for long-term management of contaminated reactor systems. The incident highlighted the importance of maintaining containment integrity and reliable cooling during fuel damage events, while demonstrating the complexity of recovery operations under high radiation conditions. The successful management of immediate safety concerns during the stabilization period provided essential time for developing comprehensive investigation and recovery plans that would eventually lead to definitive identification of the failure mechanism and implementation of corrective actions. The effective containment of radioactive materials and maintenance of adequate cooling established confidence that recovery operations could be conducted safely, despite the severity of fuel damage that had occurred. The comprehensive investigation that followed the Fermi 1 incident extended over more than 4 years and revealed fundamental flaws in reactor design philosophy, safety analysis methodology, and regulatory oversight that had profound implications for fast reactor development worldwide. The investigation combined detailed physical examination of reactor internals, metallurgical analysis of damaged components, thermal hydraulic modeling of the event sequence, and systematic review of design and operational practices that had contributed to the incident. The discovery of the loose zircaloy flow distribution plate in October 1967 provided definitive confirmation of the mechanical failure mechanism that had initiated the fuel damage sequence. The plate was found in the reactor vessel inlet plenum, positioned in a configuration consistent with partial flow blockage to the two fuel assemblies that had experienced thermal damage. Physical examination revealed that the plate had completely separated from its original mounting location and had been transported by coolant flow to a position where it could obstruct coolant inlet passages. Metallurgical analysis of the detached plate revealed fatigue crack patterns that provided crucial insight into the failure mechanism and timeline. The crack morphology indicated that failure had occurred gradually through thermal cycling and flow-induced vibration, rather than sudden mechanical overload. Crack initiation sites were located at weld joints where stress concentrations and metallurgical discontinuities created favorable conditions for fatigue crack development under cyclic loading conditions. The fatigue analysis demonstrated that thermal cycling between ambient temperature during shutdown periods and approximately 300 degrees Celsius during operation created sufficient stress range to initiate and propagate fatigue cracks over multiple operating cycles. Flow-induced vibration from sodium circulation contributed additional cyclic loading that accelerated crack propagation and ultimately led to complete separation of the plate from its mounting structure. This failure mechanism revealed critical gaps in design analysis for components classified as passive structural elements. The flow distribution plates had been analyzed for static structural loads, but had not been subjected to comprehensive fatigue analysis under combined thermal and hydraulic loading conditions. The design review process had not adequately considered the potential for mechanical failure of these plates under long-term operating conditions, despite their critical role in maintaining adequate coolant distribution. The investigation of attachment design and manufacturing practices revealed that welding procedures for the flow distribution plates were adequate for static loading conditions, but potentially inadequate for the dynamic loading environment present during reactor operation. Weld quality control and inspection procedures had not addressed fatigue resistance or long-term reliability under thermal cycling conditions because these components were not classified as safety-critical systems requiring enhanced fabrication standards. Examination of the damaged fuel assemblies provided detailed confirmation of the thermal progression that had led to fuel melting and fission product release. Metallurgical analysis revealed that peak fuel temperatures had reached approximately 1,500 degrees Celsius in localized regions, well above the melting point of metallic uranium fuel. Post-irradiation examination showed evidence of fuel melting, cladding oxidation, and structural distortion consistent with severe thermal transients under reduced coolant flow conditions. Cladding examination revealed oxidation patterns and mechanical failure modes characteristic of high-temperature exposure and thermal stress. The zircaloy cladding had experienced rapid oxidation above critical temperature thresholds, creating oxide layers that reduced effective wall thickness and degraded mechanical properties. Thermal stress from temperature gradients and differential thermal expansion had created mechanical loading that exceeded ultimate strength limits of the oxidized cladding material. The fuel damage patterns confirmed that thermal damage was localized to specific regions within two adjacent fuel assemblies, where flow restriction was most severe. Material analysis showed that fuel melting had occurred in approximately 4 to 5 fuel pins within each affected assembly, representing a small fraction of total core fuel inventory. The limited extent of damage demonstrated that thermal transients had not propagated beyond immediately affected regions during the time period before reactor shutdown. The investigation examined the adequacy of monitoring and diagnostic systems for detecting flow blockage conditions before fuel damage occurred. Analysis revealed that existing instrumentation was technically capable of providing indication of developing problems, but that diagnostic procedures were inadequate for interpreting complex symptom patterns, involving simultaneous neutron physics and thermal hydraulic anomalies. The review of operator training and emergency procedures identified significant gaps in preparation for mechanical failure events affecting reactor internals. Training scenarios had focused on equipment failures involving active systems, such as control rod drives, coolant pumps, and steam generators, rather than passive component failures that could affect core cooling. Emergency procedures provided limited guidance for diagnosing and responding to flow blockage conditions because such events were not considered credible during design development. Human factors analysis revealed that the pattern of temperature anomalies observed during months preceding the incident had created cognitive biases that led operators to dismiss genuine thermal indications as instrumentation problems. The investigation of previous anomalies had concluded that temperature readings were unreliable, creating dangerous confidence in electrical rather than thermal causation when similar symptoms reappeared during the actual incident. The regulatory review examined the adequacy of safety analysis and oversight for components not traditionally classified as safety-related systems. The Atomic Energy Commission found that design review procedures had not adequately considered the potential for mechanical failure of flow distribution components, despite their essential role in maintaining fuel cooling. The regulatory framework lacked mechanisms for identifying and analyzing safety implications of components, classified as passive structural elements. The investigation findings led to comprehensive recommendations for design modifications, operational improvements, and regulatory enhancements that would influence fast reactor development for decades following the incident. Design recommendations included improved mechanical attachment methods for internal components, enhanced monitoring systems for individual fuel assembly conditions, and modified flow distribution systems that could not create single-point failure modes affecting multiple assemblies simultaneously. Operational recommendations addressed diagnostic procedures for multi-parameter anomalies, operator training requirements for thermal hydraulic system understanding, and emergency response protocols for mechanical failure events. The recommendations emphasized the importance of comprehensive thermal hydraulic monitoring and the need for diagnostic procedures capable of distinguishing genuine plant problems from instrumentation anomalies under complex symptom conditions. Regulatory recommendations included enhanced oversight of design changes affecting reactor internals, improved requirements for safety analysis of passive components with potential safety implications, and mandatory operator training programs addressing thermal hydraulic, diagnostics, and mechanical failure scenarios. The Nuclear Regulatory Commission used the investigation findings to establish precedent for licensing review of similar facilities and to develop guidance for comprehensive safety analysis of fast reactor systems. The broader implications of the investigation extended to fundamental reactor safety philosophy and the relationship between accurate instrumentation and operational decision-making. The incident demonstrated that reactor safety depended not only on individual component reliability, but also on the adequacy of information systems connecting human cognition to reactor state under all credible operating conditions. The investigation concluded that accurate measurements could provide misleading operational guidance when diagnostic frameworks were inadequate for interpreting complex system interactions. The Fermi 1 incident established that reactor safety analysis must consider not only the reliability of individual components, but also the potential for accurate instruments to create false situational awareness when interpretation logic is optimized for familiar failure modes rather than comprehensive system understanding. The international impact of the investigation findings contributed to worldwide improvements in fast reactor design and operational practices. Technical information was shared through international organizations to ensure that lessons learned were incorporated into reactor projects in multiple countries. The incident became a foundational case study for reactor safety analysis, operator training programs, and regulatory oversight throughout the global nuclear industry. The investigation established the importance of comprehensive system analysis that considers the interaction between mechanical reliability, instrumentation adequacy, human factors, and procedural effectiveness under all credible operating conditions. The incident demonstrated that reactor safety requires not only reliable individual components, but also information architectures that provide operators with accurate situational awareness and appropriate response guidance even when accurate measurements reflect unfamiliar system conditions. The final investigation report concluded that the incident was preventable through better design practices, enhanced monitoring systems, and improved operator training, while acknowledging that the successful containment of radioactive materials demonstrated the effectiveness of defense in-depth safety principles when properly implemented. The investigation findings provided a foundation for continuous improvement in reactor design and operation that influenced nuclear safety practices for decades following the incident, establishing precedent for comprehensive safety analysis that extends beyond traditional component-focused approaches to include systematic consideration of information systems and human factors integration.